Know that feeling when you look at a list of numbers and you can just feel there's a hidden rule, a secret logic that tells you exactly what's supposed to come next? Well, today, we're going to pull back the curtain on the elegant math behind those very patterns. Let's get into it.
All right, take a quick look. For pattern A, I'm guessing you figured out the next number is 9. Pretty straightforward. And for pattern B? A little trickier, but maybe you landed on 162? If you got those, you've already got the hang of the two big ideas we're exploring. But how do we talk about these patterns with, the proper math language? It all starts with two key definitions.
First up, the basic building block, a sequence. All it is, really, is a set of numbers written in a specific order. That's it. It can be a short list, or it can go on forever. You've probably heard of the Fibonacci sequence. That's a classic example, where you add the two previous numbers to get the next one. But the main thing to remember is the sequence is the list.
Now a series, that's what happens when you take that list and you add all the numbers up. So if the sequence is the list of ingredients, the series is the final cake. It's a small difference in words, but it's a huge difference in what you're actually doing with the numbers.
Okay, let's circle back to that puzzle from the beginning. Those two patterns weren't just random. They actually represent the two most common types of patterns you're ever going to see. I like to call them the adder and the multiplier.
And this table here, it lays it all out perfectly. On one side, you have the arithmetic progression, or AP. That's our adder. The rule is simple. You just add the same number over and over. We call that number the common difference, or D. On the other side, you've got the geometric progression, or GP. That's our multiplier. Here, you multiply by the same number each time, and we call that the common ratio, or R. So one's about adding, the other's about multiplying. That's the key.
So let's really dig into the adder first and build a little toolkit for these arithmetic progressions. We're going to get two super powerful formulas, one to predict any number way down the line, and another to add them all up in a snap. So what if you wanted to know the 500th odd number? You're not going to sit there and write them all out, right? Of course not. This formula is your ultimate shortcut. All you need is the first number in the list, A, the number you keep adding, D, and the position you're looking for, N. Plug them in, and you're golden.
Finding one term is cool, but what if you need to add the first 100 terms, or the first 5,000? There has to be a better way than just mashing buttons on a calculator for an hour. And of course there is. And it's one of the most elegant little tricks in all of math.
Okay, get ready, because the genius of this is just wow. You take your sum and you write it out. Then, right underneath, you write the exact same sum but backwards. Now add those two lines together, one column at a time. Here's the magic part. Every single pair adds up to the exact same number, the first term plus the last term. And since you have n numbers in your list, you have n of these identical pairs. It's just so clever.
So after all that clever rearranging, we're left with this powerhouse of a formula. With this single tool, you can add up any arithmetic series, no matter how long, just by knowing where it starts, what it's adding by, and how many numbers you want to include.
And how powerful is it? Well, what's the sum of the first 50 odd numbers? It's exactly 2,500. No calculator, no adding one by one. We just pop in A equals 1, D equals 2, and N equals 50 into our formula, and boom, out comes the answer. That's incredible. All right, we've totally nailed the adder. Now it's time to switch gears and build the toolkit for our multiplier, the geometric progression. And trust me, this is where things can start to get really big, really fast.
The formula for finding a specific term here looks kinda similar, but you have to spot the huge difference. That little n-1 is an exponent. It's a power, and that's why these sequences can just explode. This is the math behind things like compound interest and viral growth.
So how do you add these things up? Well, it takes a different trick, but it's just as slick. You write out the sum. Then you create a second version by multiplying that entire sum by R. Now subtract that new line from the original one. And just like magic, almost everything in the middle just cancels out. All you're left with is the very first part and the very last part. And that little algebraic maneuver gives us this formula. Yeah, it looks a bit more complicated, but it's an absolute workhorse. It lets you sum up any finite geometric series with one tiny condition. That common ratio R can't be 1, because, then you'd be dividing by 0, and the universe doesn't like that.
Okay, so far so good. We can handle lists that have an end, but what happens when the list just never stops? This is where the math starts to get really, really weird and wonderful.
Let's just let that question hang in the air for a second. It sounds completely bonkers, right? If you keep adding positive numbers forever and ever,
shouldn't the total just get bigger and bigger until it's, well, infinity? It seems like common sense. But it turns out, common sense isn't always right.
Okay, let's just watch what happens with this series. 1 plus a half plus a quarter, and so on. We start at 1. Then we add a half, we get to 1.5. Add a quarter, we're at 1.75. Add an eighth, 1.875. See what's happening? The total is growing, yeah, but each step is getting smaller and smaller. It's like it's creeping up on a finish line that it gets infinitely close to, but never quite crosses. And that finish line is the number 2.
So what's the magic here? Why does this work? Let's go back to our sum formula. Remember that r to the power of n part? Well, if your r is a fraction, something between -1 and 1, like 1/2, what happens when you multiply it by itself over and over? It gets so tiny, ridiculously small. So small that when n becomes infinitely huge, that whole term basically shrinks down to 0 and just disappears.
And once that r to the n term vanishes from our big formula, the whole thing collapses into this beautifully simple equation. It's an incredible result for any of these multiplier series. As long as the multiplier is a small fraction, the sum of all its infinite terms is just the first term divided by 1 minus that multiplier.
And boom! There's the answer to our puzzle. For our series, the first term a was 1, and the ratio r was 1/2. So, 1 divided by 1 minus a half is just 1 divided by a half, which is 2. It's true. You can add up an infinite list of numbers and land on a nice, clean, finite answer.
All right, so let's do a super quick rundown. A sequence is a list. A series is a sum. Arithmetic is for adding. Geometric is for multiplying. We've got simple, powerful formulas to predict terms and find sums for both. And the biggest takeaway? Sometimes you can add numbers together forever and still end up with a finite number.
You know, that whole idea of summing to infinity, it kind of breaks your brain a little, but in the best possible way. It makes you step back and wonder, if a paradox like that can be solved so neatly, what other things in math that seem completely impossible are just waiting for us to find the right way to look at them? Makes you wonder, right?